Hello everyone. Today we are going to see the unit 3, which is on theory of metal cutting. In this we are going to see the single point cutting tool. In that, tool geometry, mechanics of shearing, orthogonal and oblique is there, shear plane angle, shear stress, strain and shear strain rate, process parameters, their effect on cutting forces, merchant circles of forces, graphical and analytical, estimation of shear force, normal shear force, friction force, normal friction force, material removal rate, cutting power is estimation, calculation of total power and specific energy, measurement of cutting forces by tool dynamometer for turning, drilling, milling and grinding operations, machinability, factors affecting machinability, tool life, tool wear, types of tool wear and remedial actions, cutting fluid and their types, effect of process parameters on tool life, Taylor's tool life relation, that is derivation along with numericals, and the economics of machining, that is optimum cutting speed for maximum production rate, optimum cutting speed for minimum cost. Okay, so let us start with single point cutting tool. So this is the geometry of a single point cutting tool. Okay, so American system angles are specified independently of the position of the cutting edge and therefore does not give indication of the behavior of tool in practice. Advantage is the simplicity of its use in grinding of the single point cutting tools. The tool cannot be ground accurately to the back rake and side rake without using equations or curves. So let us see the tool geometry. So here you can see the tool geometry, the views of single point cutting tool, back rake angle, side rake angle, end relief angle, side relief angle, end cutting edge angle, side cutting edge angle, nose radius. Now here we are going to see the mechanism of machining. Here you can see as the workpiece is moving in this direction and tool is moving in opposite direction, and here the chip formation is there. Okay, so let us see the mechanics of machining, orthogonal and oblique cutting. The two basic methods of metal cutting using a single point tool are the orthogonal, which is 2D, and the oblique, which is 3D. Orthogonal cutting takes place when the cutting face of the tool is 90 degree to the line of action of the tool. If the cutting face is inclined at an angle less than 90 degree to the line of action of the tool, the cutting action is known as oblique cutting. Okay, so here there are types of chips in machining: discontinuous chip or segmented chip, continuous chip with built-up edge, serrated chip. So if you see the discontinuous chip is here, it occurs mostly in the brittle work materials, that is in cast irons, where the low cutting speeds and large speed and depth of cut, and it occurs due to low cutting speed, large speed and depth of cut, and high tool chip friction is there. Okay, so here tool and chip friction is high. So and here if you see the whatever the chip is there, after chip formation irregular surface is there due to chip segmentation. Okay, so next we are going to see the continuous chip. In continuous chip it occurs during ductile work materials, for example low carbon steel. Okay, and during this the high cutting speed is there and small pits and depths. Okay, and here the sharp cutting edge on the tool, and if you and you can see there is low tool and chip friction. Okay, and due to that continuous chip the finish is a good finish. Okay, and next, that is continuous with built up edge. This occurs in ductile material while removing the ductile material, and it occurs at low to medium cutting speed, and the tool chip friction causes portion of chip to adhere rake face. Okay. Built up edge formation is cyclical. It forms, then breaks off. It forms and then breaks off. So particles of built up edge which sometimes sticks to the surfaces over here. Okay. So next, that is serrated chip. This is what semi-continuous and sawtooth appearance is there. This chip's appearance is a sawtooth appearance, and this cyclical chip formation of alternating high shear strain than low shear strain, and most closely associated with difficult to machine metals at high cutting speed. Okay, so in such a way, serrated chip forms, which looks as a sawtooth appearance. Okay, now let us see the cutting conditions in machining. The three dimensions of a machining process: one is cutting speed, primary motion; second is feed, secondary motion; third is depth of cut, penetration of tool below original work surface. For certain operations, material removal rate can be found as MRR is equal to VFD, where V is equal to cutting speed, F is equal to feed, D is equal to depth of cut. So in this diagram we can see the V, that is the cutting speed, is there, F feed is there, D depth of cut is there. Okay, so next, mechanics of machining. It involves study of various forces and velocities that are related to the process of machining. So here you can see the thin shear zone at high speed, and here the thick shear zone at low speed for soft materials. And here the analysis of chip forming. Okay, figure shows the shear plane model of continuous chip formation. Okay, now further we are going to see the calculation of shear angle. Here you can see the phi is there. Phi is nothing but shear angle, yn is normal rake angle, ls is length of shear plane, ac is uncut chip thickness, a0 is chip thickness. Many times what happens, at chip thickness can be taken as t, and uncut chip thickness can be taken as a tc also. So it depends on the us what notations we are going to use it. Okay, so here it is used as a AC and A0. FC is cutting force, Fs is shear force, Ft is thrust force. So here you can see Fs shear force is there, and Fc cutting force, it is horizontal, Ft thrust force is there. Okay, now we are going to see the calculation of shear angle. So phi, here you can see phi is a shear angle over here. Okay, so let us calculate the shear angle. So length of shear zone, that is AC upon sin phi, A0 upon cos phi minus I. Then after rearrangement we will get the RC cos gamma NE up into 1 minus RC up into sin gamma NE. Here you can use other notations also instead of gamma, theta, or whatever you feel. Okay, but you are supposed to mention that the meaning of that symbol. Okay, so let us see further. This is the calculation of chip thickness, where MC is mass of chip specimen, LC is length of chip specimen, AW is width of chip, rho is density of chip, A0 is a chip thickness. So A0 chip thickness can be calculated is equal to MC upon LC into AW rho. Okay, orthogonal cutting theory. Thin shear zone is assumed. The cutting edge inclination angle is equal to 0 degree. Chip flow angle 0 degree. Cutting edge extend on both side of workpiece. Okay, so here next the velocity relation. So by taking sin phi is equal to CD upon CA, sin phi is equal to CD upon CA. Okay, in such a way, by putting all the values, we will get the answer is Vs is equal to V cos gamma ne upon cos into bracket phi minus gamma ne. Okay, so next, orthogonal cutting model, a simplified 2D model of machining that describes the mechanics of machining fairly accurately. So in this, the chip thickness ratio is equal to R is equal to E0 upon AC, where R is equal to chip thickness ratio, E0 is equal to thickness of the chip prior to chip formation, and AC is equal to chip thickness after separation. Chip thickness after cut is always greater than before, so chip ratio is always less than 1. Okay, remember, chip thickness after cut is always greater than before, so chip ratio is always less than 1. Now here there is a strain and strain rate determination. So by using this method, you can calculate shear strain rate. Okay, now next, this is the realistic view of chip formation showing the shear zone rather than shear plane. Also shown is the secondary shear zone resulting from tool chip formation. Okay, now let us see next the merchant circle analysis. So this is what the merchant circle diagram. Now let us see the forces acting on chip. So friction force and normal force to friction, and shear force Fs and normal force to shear Fn. So these are the forces acting on chip. Okay, and the next, the resultant forces, vector addition of F and then resultant R. Vector addition of Fs and Fn is equal to resultant R dash. So forces acting on the chip must be in balance. R dash must be equal in magnitude to R dash must be opposite in direction to R dash must be collinear with R. Now let us see the coefficient of friction. Coefficient of friction between tool and chip, that is mu is equal to F upon N, and frictional angle related to coefficient of friction as follows, that is mu is equal to tan beta. And shear stress, so here shear stress acting on along the shear plane, that is S is equal to Fs upon As. As is nothing but area of the shear plane, so As is equal to T0W upon sin phi. Shear stress is equal to shear strength of work material during cutting. Now let us see the cutting force and thrust force. So forces F and Fs and Fn cannot be directly measured. Forces acting on the tool that can be measured are cutting force and thrust force. So figure shows the forces in metal cutting. Forces acting on the tool that can be measured, that is cutting force and thrust force. Let us see the forces in metal cutting. Equation can be derived to relate the forces that can be measured to the forces that can be measured. F is equal to Fc sin alpha plus Ft cos alpha. N is equal to Fc cos alpha minus Ft sin alpha. Fs is equal to Fc cos phi minus Ft sin phi. Fn is equal to Fc sin phi plus Ft cos phi. Based on these calculated force, shear stress and coefficient friction can be determined. Now the Merchant equation of all the possible angles at which shear deformation could occur, the work material will select a shear plane angle which minimizes energy given by phi is equal to 45 plus alpha by 2 minus beta by 2 divided by using Merchant based on orthogonal cutting, but validity extends to 3D machining. What the Merchant equation tells us: to increase shear plane angle, increase the rack angle, and also to increase shear plane angle, reduce the friction angle or coefficient of friction. And higher shear plane angle means smaller shear plane, which means lower shear force. Result: lower cutting force, power, temperature, all of which means easier machining. So here the effect of shear plane is shown over here. Now power and energy relationship. A machining operation requires power. The power to perform machining can be computed from Pc is equal to Fc into V, where Pc is cutting power, Fc is cutting force, and V is the cutting speed. So gross power to operate the machine tool Pg or HPG is given by Pg is equal to Pc upon E, or HPG is equal to HPC upon E, where E is equal to mechanical energy of machine tool. So typical E for machine tool is considered as approximately around 90%. Unit power in machining useful to convert power into power per unit volume rate of metal cut. So called as the unit power, and its formula is P is equal to Pc upon MRR, where MRR is material removal rate. Specific energy in machining. Unit power is also known as the specific energy U, which is equal to Pu is equal to Fc upon T0 into W. Units for specific energy are typically Newton meter per mm cube or joule per mm cube. Now let us see the factors affecting the cutting forces. First, material of the workpiece, cutting speed, feed, depth of cut, tool geometry, tool conditions. These are the factors which are affects the cutting forces. So measurement of cutting forces. So measurement can be done by using mechanical dynamometer, strain gauge type dynamometer, pneumatic and hydraulic dynamometer, piezoelectric dynamometers, electrical dynamometers. So here you can see the measurement of cutting force in turning. So here the magnetic sensor is connected to the tool, and the test piece is there. Okay, so to it the charge amplifier is connected, and to the tool set magnetic sensor is there for synchronization. So in and here the dynamometer is there, so you can measure the cutting forces. Now let us see in milling. In milling you can see at the bottom of the workpiece the dynamometer is there. It is connected to the charge amplifier, then data acquisition system, then computer. So whatever the force which comes on the workpiece, it is the force is shown on the computer, and same in the drilling machine. Okay, so here accelerometer is used, accelerometer, and again at the bottom dynamometer is there. Okay, so in such a way we'll get the graph in such a way, feed rate versus cutting force. Now next let us see the machinability. It is defined in terms of surface finish and surface integrity, tool life, force and power required, the level of difficulty in chip control. So good machinability indicates good surface finish and surface integrity, a long tool life, and low force and power requirements. Machinability ratings are available for each type of material and its condition. So let us see the factors affecting machinability of metals. Material of workpiece, hardness, tensile properties, strain hardenability. tool material, size and shape of the tool, type of machining operation, size, shape and velocity of cut, type and quality of machine used, quality of lubricant used in machining, friction between chip and tool, shearing strength of workpiece material. Now let us see the evaluation of machinability factors: tool life, form and size of chip and shear angle, cutting forces, power consumption, surface finish, cutting temperature, MRR per tool grind, that is material removal rate, rate of cutting under standard force, dimensional accuracy. So these are the factors for the evaluation of machinability. Now machinability decreases with increase in tensile strength and hardness. Machinability of a material is assessed by any of the following: tool life, limiting material removal rate at which the material can be machined for standard short tool life, cutting force, surface finish, chip shape. Now let us see the machinability index is equal to Vt upon Vs into 100. Vt is nothing but a cutting speed of metal for 1 minute tool life. Vs is cutting speed of standard free cutting steel for 1 minute tool life. So here we can see the machinability index. Now let us see the machinability of ferrous metals. Steels: if a carbon steel is too ductile, chip chip formation can produce built up edge leading to poor surface finish. If too hard, it can cause abrasive wear of the tool because of the presence of carbides in the steel. In leaded steels, a high percentage of lead solidifies at the tips of manganese sulfide inclusions. Calcium dioxide oxidized steels contain oxide flakes of calcium. Silicates CSO that reduce the strength of the secondary shear zone and decrease tool chip interfere friction and wear. Now, effects of various elements in steel. Presence of aluminum and silicon is harmful as it combine with oxygen to form aluminum oxide and silicates, which are hard and abrasive. Thus, tool wear increases and machinability reduces. Stainless steel: austenitic 300 series steels are difficult to machine. Ferritic stainless steels, also 300 series, have good machinability. Martensitic steels are abrasive, which is having 400 series. Aluminum is very easy to machine. Beryllium requires machining in a controlled environment. Cobalt based alloys require sharp abrasion resistant to materials and low feeds and speeds. Copper can be difficult to machine because of built up edge formation. Magnesium is very easy to machine with good surface finish and prolonged tool life. Titanium and its alloys have very poor thermal conductivity. Tungsten is brittle, strong and very abrasive. So tool life: useful cutting tool life of tool expressed in time. Time required: time period measured from start of cut to failure of the tool or end of the tool. Time period between two consecutive resharpenings or replacements. This is called as a tool lives. Now let us see the ways of measuring tool life. Number of pieces of work machined, total volume of material removed, total length of cut, limiting value of surface finish, increase in cutting forces, dimensional accuracy, overheating and fuming, presence of chatter. These are the ways of measuring tool lives. Now let us see the modes of tool failure. First, temperature failure. So plastic deformation due to high temperature, cracking due to the thermal stresses at rupture of the tool point, chipping of tool edge, crumbling, gradual wear at tool point, flank and crater wear. Tool wear. Tool wear causes the tool to lose its original shape. In effective cutting, tool needs to be resharpened. Now let us see the causes. Attrition wear, that is at low cutting speeds, flow of material past cutting edge is irregular and less streamlined. Built up edge formed and discontinuous contact with the tool. Fragments of tools are torn from the tool's surface intermittently. Slow and interrupted cutting high. Presence of vibrations high, found in carbide tools at low cutting speeds, high in attrition wear. And in diffusion wear, diffusion of metal and carbon atoms from the tool surface into the workpiece and chip due to high temperature, high pressure, rapid flow of chip and workpiece past the tool. Diffusion rate depends on the metallurgical relationship. It is significant in carbide tools. Abrasive wear, it is due to presence of hard materials in workpiece material. Strain hardening induced in the chip and workpiece due to plastic formation. It contributes to flank wear. Effects can be reduced by fine grain size of the tool and lower percentage of cobalt. Electrochemical wear, when ions are passed between tool and workpiece, oxidation of the tool surface occurs. It breakdown of tool material at chip tool interface. Chemical wear, interaction between tool and work material. Plastics with carbide tools and cutting fluids. Due to this, the chemical wear occurs. Plastic deformation, when high compressive stresses acts on tool recface, tool deformed downwards, reduces relief angle, modifies tool geometry and accelerates other wear processes. So thermal cracking, it occurs due to cyclic thermostresses at cutting edge, comb cracks, transverse cracks. So the chipping of tool occurs. Now this is the geometry of tool wear. The flank wear is here. You can see the flank wear, edge wear, crater wear, which is as a face wear. So flank wear is the tool slides over the surface of the workpiece and friction is developed due to friction and abrasion. Adhesion between workpiece and tool built up edge forms. It starts widening along the clearance face independent of cutting conditions and tool and workpiece materials, brittle and discontinuous chips, and increases as speed is increased. So primary stage rapid wear due to very high stress at tool point. Wear rate is more or less linear in the secondary stage. Tertiary stage wear rate increases rapidly resulting in catastrophic failure. So here flank wear is occur. Now crater wear, direct contact of tool and workpiece. It forms cavity mostly in ductile materials, cutting edge chips forms, so the cavity forms over here. Initiates rapid rupture near to nose. It leads to weakening of the tool, increase in cutting temperature and cutting forces and friction. Okay, now let us see the measurement of tool life. So time for total destruction in case of high speed steel or time to produce 0.75 mm of the carbide tool. So tool life expressed by Taylor's equation, that is Vt raised to b is equal to c. At also many times instead of b, n will be also given, that is Vt raised to n is equal to c. V is equal to cutting speed in centimeter per minute. T is equal to tool life in minute. B is equal to constant 0.1 for HSS and C is equal to 50 for HSS. Cemented carbide B is equal to 0.125, C is equal to 100. So tool life expressed in volume of metal removed, L is equal to TV into FD. So measurement of tool life can be measured by following methods, that is diamond indenter technique, radioactive techniques, test at elevated cutting speed, facing test, test with low wear criteria. Okay, now factors affecting the tool life: cutting speed, physical properties of workpiece, area of cut, ratio of feet to depth of cut, shape and angles of tool, tool material and heat treatment, nature and quantity of coolants, rigidity of tool and workpiece. So here we are going to see the MCQs related to this topic. Okay, so let us see the MCQ on finishing process. Okay.